well, here goes. Quite literally, well, okay, not quite literally, but probably absolutely nothing. I'm doing something really incredibly stupid. Okay, let me actually get some music on first. Yeah, this is a really, really bad idea. Basically, I'm going to try and... Basically, 3b1b's a while back put out a video discussing problem solving and finding the average shadow area of a cube. And I really... It looked kind of interesting because it was a long video, and it's something I've kind of done stuff related to before. So, for instance... a while back, for something I was working on, I attempted... Okay, let's see if I can draw like this. I attempted a problem where I basically had the following. I took the corner of the cube, looked something like this, and I basically asked the question, okay, how many times will light bounce off this? Or what proportion of the time will light bounce off this 3 times before leaving the cube? And it turns out this becomes equivalent to drawing a... Oh, wow, I'm bad at drawing. I knew that before starting this. It's not really a surprise. It becomes equivalent to drawing a shape that looks something like this. And asking the question, okay, if I look at the shape from a particular angle, what is the area I see which has 3 of these squares I'm drawing in 3D, which is 3 of them intersecting? And basically, so for this instance, I'd be looking at this area. Oh, no, I'm bad. I'd be looking at this area. And so basically, yeah, it is literally, I can hear a bell outside chiming midnight. It is my first day back at uni. I am an idiot who should not be trying this from so late. But yeah, basically, I took a look at that problem, and this, that was honestly painful. It resulted in an absolutely disgusting problem. I never want to move this to my life. And so, obviously, I'm doing the completely logical thing of trying to string me attempting this problem. I think I can do it. I've got some guesses, but what I also want to do is I want to try and do it in a fun way. So I've watched like the very beginning of the video, where basically 3b1b's says, okay, we've got 2 people, Alice and Bob, and they both approach problems in a different way. One's far more mechanistic, like very targeted at solving the problem, arguably more likely to get it done. One's very holistic and is more likely to find something more general out. And so I'm just going to try to solve it how I would. The way I tend to solve problems is I tend to distract myself by looking for generality and shortcuts, which I guess kind of is like Alice, but I don't tend to actually look for general principles so much. I do tend to focus quite heavily on what I'm aiming for, but I will try and do anything I can to make my life a little bit simpler. So, firstly, I'm going to be doing a bit of drawing with this. That's largely going to be set up the problem. I guess I also can't see at the moment whether or not anyone is replying to me, because I don't actually have... I spent ages getting my old laptop up for this, so I'd be able to watch chat on one other screen. I feel I should also turn the volume of this music down a little bit more. Let me know how it works. I mean, this is... I am recording this fairly late, so I should not be too loud for other people. Epic late night math. Indeed, Sale. Indeed. Okay, so my first thought is basically it's to simplify the problem down. So specifically, we're dealing with a cube. A cube I can split up into 6 faces. But what's really important... Oh, no, okay. Let's define what so I have briefly... yes, turn the music down. Okay, yeah, I've turned the music down quite a lot. Let me know if that works better for yourself. From my single viewer for the moment. So yeah, so basically my idea is... So yeah, the problem is basically we have a cube, and we're going to find the average, and we've got a light shining. It's shining from infinity, so the rays are all parallel to one another, and we want to work out the area of the shadow, which from the thumbnail he drew looks something hexagonal. And we want to work out, as we move this around, we want to work out what the average area of the shadow is. Now, I should say there's a relatively famous paradox here, which I should mention to start, which is how to randomly select points in a circle. If I randomly select a angle and a radius, then what I find is that I tend to get points that are more clustered near the centre, because changing the angle when you're near the centre doesn't change how far the points are spread out as much, and therefore it really matters how you define the variables you're averaging over. That would... Right now I've got to undo rather a lot. But yeah, so specifically I want to begin... Yeah, you can see I was uncertain whether or not to capitalise 3b1b's to begin with. But yeah, so I'm going to begin by defining this, and basically what I'm going to say is that if we imagine that our light source is... Well, we can either rotate our light source to the cube. Let's just imagine I've got this single ray that is passing through the centre of my cube at the origin and going out the other side. I'm going to say that I'm averaging so that all equal solid areas, solid angles taken up by this cube are equal. Basically, taken up by rays are equal. In other words, the probability that I'm going to look at a ray will pass, or the number of rays that will pass through a particular area on the sphere when I take the average, will be proportional to the area of that sphere, and that's independent of where that is. I feel I should just say that before I get started. So now, how do I begin solving the problem? Well, my first thought is very mechanistic, and I want to come up with a better way of doing this, but a fairly quick solution to the problem is... Why can I not draw a cube? Quick solution to the problem, or at least way of getting enough maths down that I think the problem would come... I think it will be relatively easily solved from this, is to split the cube up into several faces. Now, when I do this, I'm going to note that not all of these faces are important. Specifically, I only actually ever need to consider half of them. So if you imagine, I guess it's kind of hard to see. I'm imagining the sun is behind the cube here, and yeah, I'm thinking of it as the sun. And it's sending out rays of light that are kind of coming towards us. That means that the light is going to hit the following faces. It's going to hit this face, it's going to hit this face, and it's going to hit this face. And it's not going to hit this face, or this face. Now, this is really important because this is going to be true no matter what orientation I'm at. We can actually see that I'm always only ever going to hit 3 of the faces. And what this means is that we don't need to consider stuff we would need to consider in more complex problems. Specifically, I don't need to consider, I guess it's probably related to some sort of convex hull argument, actually. Actually, it must be exactly related to that. That's cool. Okay, so there's some sort of relationship to the hull of a convex polyhedra. Whether or not a polyhedra is convex, or just any 3D shape is convex. But yeah. So yeah, the idea is that if you imagine, let's just consider this in 2D to begin with. You imagine I have a... it actually kind of matters how I'll draw the square for this. If you imagine I have a square like this, there is no place, there is no arrow I can draw where it will ever illuminate 2 sides at once. If you, I guess I could prove this mathematically quite rigorously by just saying that in order to be illuminating this side, we need to have a non-zero component, or we need to have a component of the light. So if we've got the normal to this side being n, we need to have some component of the light. We need to have, so imagine I've got the light moving in at a, I'm a physicist, so I'm instantly going for a k for this, but I need to ensure that n dot k is necessarily less than or equal to 0, because basically what that means is that the light isn't coming from this side. But I mean, you can quite easily see that if these two lines are parallel to one another. Was that the symbol for parallel? It's been so long I forget. I have not had to draw parallel for quite a while, like I always do. Stuff like this and have parallel to. Okay, but I forget what that actually is. Like when you're drawing geometric diagrams. But what we can notice is that the normal on this side is minus the normal on the other side, and therefore you can't simultaneously have this and this. I.e., you can simultaneously have the light coming towards both sides, unless, and there's one counterexample, unless we notice that we're actually dealing with non-strict inequalities, and what if you just have both of those equal? Well, if both of those are equal, what this really means is that our light is coming. It's, again, I mean, I could have done this geometrically. I've gone very algebraic, which I guess wasn't really necessary. Well, it completely wasn't necessary. Basically, the point is, the only way you can have light that in any way stands, that isn't coming from the wrong side, and that isn't coming from the wrong side, means it can't be at an angle to either of them. So it can't be coming like this, and it can't be coming like that. The only thing you have which achieves that is light which is going like this. But if we do have light going like that, well, okay, you can, in this Platonic universe in which we imagine we're living, we don't have diffraction or anything, this light's just travelling straight, then, well, this isn't contributing to a shadow. The light only sees the square, the light basically just only sees this one line. And so, in other words, what we're going to do is we're going to begin, or the easiest way I can think to begin, is to begin by setting up a cube looking something like this. And I'm only going to consider 3 faces of this cube. I'm also... okay, let's... great, I can't. Okay, apologies while I quickly delete a message in chat. Why is someone putting like random links in a video by some guy who's got like barely any and I'm not logged into the right account to delete this. An account that's got like no one viewing it. Why would you bother doing that? You're not going to get anyone. Okay, staff. I apologise for this delay. I prefer to remove this now rather than later. Wow, I've got multiple people. Carry on. So let's hide users on this channel. There we are. Okay, cool. So back to what we were doing. So what we can now do is we can now notice another trick, which is actually what happens if I consider light coming from the opposite direction. And I want to be a little bit careful in how I do this because I have a relatively clear idea of what I'm about to say, but I want to make this convincing. So what I'm doing is I've considered we can assume that light is, let's say for the moment, coming from, well, so it's coming towards this point. We can then say, okay, well, the light's only going to hit these 3 pieces. But what we can also say is, well, I guess I should go back to, I'm going through this quite slowly, so I apologise. For the one person who's viewing this, this is probably all incredibly obvious. But because I know Zayop has done maths and stuff like this, but I'm doing this because I think it's kind of good experience explaining what I'm doing and trying to make something hopefully quite understandable. So what I'm now going to do is I'm now going to note a bit of a symmetry, which is a symmetry between light coming in this direction and symmetry between light coming at the same angle in the other direction. And what I'm going to note is that, in particular, this shape is closed, I left it open there, and I did leave it open for a reason. The reason I left it open was to note that, well, wait a second. We can normally split this up into two different faces. But note something. If this section here is completely blocking the light from reaching this section, and this section, and vice versa, it must hold that the shadows generated due to these two things are precisely equivalent. And that begins to let us simplify things down a little bit, which means that basically I can actually, if I'm considering a cube, I can consider only this. And I can consider, or okay, in this instance, if I consider a square, I can consider only this. And if I consider, okay, that's not quite true. Should be accurate. I can consider only this. And if I consider something moving around, well, what do I get? Well, whilst it's in this position, okay, that's... Ah, no. Okay. This is where my logic falls down. No, it doesn't. No, it doesn't. This logic would fall down if this were a finite distance away. So, okay, the issue I was concerned about was, okay, what if my light's here? The light's then coming out like this. And if I'm including this wall, well then I have a little bit of an issue because there wouldn't be any light reaching that. But if I do anything in the maths that includes that wall, I would be assuming light's reaching it. But that's fine, we're not doing that because, again, our light's coming from infinity. So, specifically, if we're in any area, say, where the light source is not hitting either of these walls, so our light's coming inwards from here. So if we're in either area where the light isn't hitting either of those back walls, then we've got this nice equivalence. But we have another equivalence, which is that we're not interested in where the shadow is. We're only interested in its area. And therefore, I can equally, let's try drawing rather than erasing, I can equally consider this wall or this wall. The light's still coming at it from the same angle. Doesn't really make any difference. And that I think is quite cool, and that's quite interesting, and that begins putting us in the right direction to actually solve this problem. Because what we've established is that all that really matters, it matters that we aren't double counting. It matters that if we're counting this face, or counting the shadow generated by this face, that we're not also saying that a second shadow is being generated by this face here, because, well, there's no light reaching that because it's only the shadow of the first one. But what we can also state is that, well, yeah, we can split up the problem into something like this, but it also doesn't matter where these are. I can just have these two walls being in completely random places, and the maths will work the same because their shadows don't interact, because they're joint. If they were, okay, they might in certain circumstances. If you imagine here, the light's coming like this, but in this specific instance, one of my earlier assumptions about us having a convex hull doesn't hold. So or this shape being a convex hull doesn't hold. Specifically, what I mean by a convex hull is, well, effectively it's exactly equivalent to this, i.e. if I draw a line between any two, so let's imagine the following shape and compare it to this shape. That's a rectangle. If you imagine drawing a line between any two points, well, here I can actually, you basically have the property, can you draw a line between 2 points that doesn't lie inside the shape? And here I definitely can. Whereas with this rectangle over here, I can't. So that's what I mean when I say something is convex, and in the particular instance of our cube is convex. There's no way of drawing a line between any 2 points that lie on the cube that don't go within it. And therefore, what I'm going to say is I'm going to treat all the sides of this cube completely independently. I then have another trick I can pull. Let's be clear, I'm actually, this stage is something that I hadn't even considered beforehand. But the second trick I'm going to think about is the following, which is the fact that we've also got another property. We've got rotational symmetry. And so, in particular, okay, let's let's start by writing this. Let's start by writing this out for one face. And how am I going to do this? Well, it turns out there's a relatively simple mathematical trick to working out the area of a shadow, and it is to consider the shape you're looking at, to take its area. In this instance, let's say A. To take the normal of the light, or in my instance, I'm going to call it K, because again, physicist, physics habits die hard. So I'm going to take the direction of the incoming light. I'm going to take the normal to the surface, i.e. the perpendicular to the surface, and I'm going to take the dot product of them. Unfortunately, there's only, I guess, so much I can explain in this video, this live stream, so I'm not going to explain precisely what the dot product is or how it comes about, which isn't not. I feel like I really should, to make this as accessible as possible. Best way of explaining it. Okay, effectively the dot product says, very, very quickly, the dot product says, imagine I'm pushing a mass up some slope. I've got a force, I've got gravity, I've got the force of gravity pushing down, but I'm pushing this mass in a direction that isn't just directly upwards. If I were pushing it directly upwards, so the motion, let's say, displacement D prime, gravitational force G. So if I were pushing directly upwards, the formula would be mgh, the formula for the amount of energy stored, and basically, let's go with the energy stored. So by pushing it up, it's not h, I guess, sorry. This is one of the instances where you're so used to writing a certain formula. So we've got mgd. But what happens if we're instead pushing an angle? Well, the actual energy I've put in is going to be related to the height I've raised. I've raised this, well, m is just the mass of the object. So if I'm considering in more general terms, let's say I'm now pushing it in this direction. Well, if I know the angle theta of this slope, I can work out, okay, how high have I pushed it? That's going to be, the height of this is going to be d primed cosine of cosine adjacent hypotenuse. No, I'm completely wrong. Sine. I'm talking nonsense and no. Okay, why am I bad? Why can I not do maths? Someone please explain. Because I'm messing this up. This is why I should not start at midnight. I guess I'm just defining an angle in the wrong way. I should have defined theta about another position. The annoying thing about that is it makes it less clear. No. Okay, yeah. It's better to define theta about here, and why is that better? Well, it's related more directly to this angle here, the angle between these two, or more importantly, this angle, and so effectively it's related to how far is D away from being parallel. Okay, you could say more accurately it's like all of this, that complete angle, but yeah, it turns out the way I've defined stuff with sines and the cosine, that doesn't really matter. Anyway, so yeah, your very quick description is that here we've got d cosine of theta. That's the height we lift it. We've lifted at a height of that. We know the energy stored by height of that, and you end up with this thing, which is the energy stored is equal to d prime g cos theta, and then multiplied by the mass. And that's just the mass times gravity times the amount we've lifted up. It's the same thing as here, but we haven't lifted it up as far. But what we then note is that basically this comes up an awful lot, and so we decide to define this as okay, there's a negative sign which crops up because of how I've defined d and g, and well, precisely how I actually define theta here. We basically end up deciding to do something like this. This isn't actually equal. There should be really a negative sign here. This just comes about from how I've defined theta. But the point is, we end up with this notion of a dot product, and it's somehow related to how close two angles are to one another. And what you can show is that, well, I mean, it's intuitively, or how close two vectors are to one another. And it's intuitively quite obvious, right? Because, well, if these two vectors are as close to one another as they possibly can, i.e. k is parallel to n, that corresponds to light that's just coming directly. That's a really bad perpendicular. Light that's just coming directly onto a thing. Well, of course that's going to and that's going to have a shadow that looks like this, as opposed to if I do this, a shadow that I need to define more stuff. Oh no. Okay, I need to actually check. Oh no, okay, we're dealing with all possible orientations of a cube. That's actually really important. We're not just moving the light around and having a flat surface. So in particular, the shadow due to this, and the shadow due to the same thing, but where I rotate this by a certain amount, so the surface remains the same. That's something important that I nearly missed, and would have made it incorrect. So even if I keep the length of this thing the same, you can see that as I change that, the shadow decreases, and you can go to the really extreme example where I make this perpendicular. I keep forgetting to change back. Where I make this perpendicular, and you can see, well, the shadow goes to basically 0. Okay, and so this is the trick I'm going to use. I'm going to use the fact that the area of a shadow generated like this is equal to k hat dotted with n hat. Okay, there should be a negative sign here, really. K hat n hat a. And normally this is just written as normally that's just written. That's just defined. Well, we define the following. We define a vector such that we can do this. Okay, this is all relatively common. I've spent a little bit of time going over that. But yeah, this is now going to be the area of the shadow. And that's what we want. So, after really a lot of preamble, we've just come up with the shadow of the face of a cube. Now, what I can do is I can begin doing a little bit more of the tedious stuff. So in particular, okay, I should think about how exactly I want to begin to phrase this. So firstly, what I've done is I've noted that when I'm dealing with areas of a shadow, I can deal with all of the faces completely independently. And I can just move them off, I can separate them. In fact, I don't even need to calculate their averages at the same time. I can do the experiment with one face, do the experiment with the next face, and do the experiment with the final face. But here's a trick. What we can also do is we can note that, well, there's no difference. I guess I should go back to 2D. There's no difference between measuring this face like this and finding the area of that shadow. I guess I should really draw. I should be more precise and draw the direction of the light rather than the light source, because otherwise that would be confusing. There's no difference to considering that as to considering this. And so, if I'm going to go around the entire surface of this, well, then considering this from this angle, if I'm going to do it from both angles at some point, like this and like this, and if I'm going to sum those two results, well, that's exactly the same as if I just took. So doing this system from both of these directions is the same. This problem here is equivalent to both of these problems, but the thing is, both of those problems, you can see they're just rotated from one another by 90 degrees. They're the same. So all I need to do is calculate this and multiply it by 2. And in the case, because there are two things which are in this instance, I guess, edges, but in 3D faces, which are in some sense equivalent, and I can do exactly the same thing with this cube. I can take one face, I can rotate my light around it, and then I can find the average area, and I can just multiply that by 3. And so that's going to be my first solution to this problem, because I think that simplifies the problem down quite a bit. I don't think that is the neat solution 3 blue 1 brown would have presented. I almost guarantee it will not be, but I think that's a reasonable starting place for a solution. So, okay, so how am I going to do this? Let's return to, still in drawing mode, let's return to maths. So, alright, firstly what I need to do is I need to define in some neat and some intelligible way the direction the light is coming in. I'm going to continue to define this via k hat. This is not like an exactly conventional defining it, so wait for that to come up. Okay, now what I'm going to do is I'm going to move into spherical polar coordinates. Well, this is I should also for my own. Oh, okay, ignore that. I thought I was in the wrong font because sometimes it's a long story. But anyway, what I'm going to do is I'm going to actually just Google spherical polar coordinates, because I do sometimes mess this up. No, I should be able to do this without messing things up. So basically, I'm going to I need to basically define a way. Let's leave the equation. Because if I'm just Googling something, then I'm not explaining it well. So let's actually explain what it's I'm precisely doing. Imagine I've got the Earth, and I'm going to define some lines of latitude and some lines of longitude. What I'm going to say is that the angle I've moved down from the very top, this isn't how latitude is defined, but I don't care. I'm going to find the angle I've moved down as theta, and I'm going to define the angle I've moved around from some fixed starting point as var phi. I always draw my var phi's backwards, and I know most people don't pronounce var phi, but I spend so much time typing on this that I ended up doing so. Now, a bit of trigonometry. I guess I might as well leave this up for a second. A bit of trigonometry basically shows us that, let's turn to equation typing. Okay, there's one really easy component to get out of this, and that is the fact that the z component, so I'm defining z as being the vertical here, the z component is going to be equal to cosine of theta. Why is that? Well, it's because it's maximum when theta is 0, it's minimum when theta is 180 degrees or pi, and it is 0 when we're at pi over 2. Okay, then I'm going to basically put a trick here, which is that I know this needs to be normalized, and okay, yeah. I don't have time to go through everything here, I don't think. So I'm just going to basically say you can convince yourselves that this is a parameterization. To leave that like this, and then make this cosine. Depending on your convention, or depending on where you're looking, you may see these two written in another order. It doesn't make any difference. Honestly, I'm going to skim past some of the details of this maths. All you should notice is that, well, my position on the x and z, or the x and y axis, well, that's kind of about this horizontal, or about this equatorial. The plane parallel to the equatorial plane is going to be the x and z axis, or the x and y axis, and you can see that that is perpendicular to the z axis, and therefore you should expect that your cosines will go to sines, and then we're just in standard spherical or standard polar coordinates, and we've got our sine and our cosine terms. I guess if we are drawing an analogy to standard polar coordinates, I guess I should do that. Because that's kind of your more typical coordinates. I think I like that less. I'm going to go back to what it was before, because that then preserves just a tiny bit more symmetry. And one way I tend to approach things in physics is always write everything with as much symmetry as you can at all points in time, because it makes your life so much easier. So what I'm now going to do is basically what I said I was going to do. I'm going to define Right, this can't be. Is this just going to work? So the thing is, if I'm rotating, oh yeah, this seems a little too easy. Yeah, no, okay. If I'm rotating my light source around, so I've got where's dot? I'm in hat. Actually, I guess I'll just define A. So if I'm rotating my light source around, what I'm going to want to do is I'm going to want to hold my plane fixed. And if I'm holding my plane fixed, again, this produces simplification, which is, well, as has already been established, if we're going in all directions anyway, I can pick this to be oriented in whichever direction I want. In particular, I can pick the normal to be facing in the Z direction, and that's going to be quite nice because we've already established I'm going to be taking the dot product of K and A. If I'm taking the dot product of K and A, okay, yeah, there, I'm not going to go into details on this calculation. If you haven't seen the dot product before, basically, the way you handle the dot product is it's the sum of the products of the components with one another. And so in this instance, we're only going to be left with an A cos of theta. I meant to do a backslash. Okay, got a cosine of theta. And this looks almost too easy to be true. We now need to come up with an area element for the surface of our sphere, because so we need to ensure that when we take an average, we are averaging all areas equally. I'm going to just define my sphere. I'm going to define my sphere to be a unit sphere, because we're literally, it doesn't make a shred of difference. We'll end up cancelling it later on anyway. So I'm going to say, oh no. I've seen an issue. An issue which I need to think about quite carefully. So, here's the issue. The issue is that areas are positive. Haha. Okay, this is cool. Okay, I can correct for this. This is fine. But it's nice to be tricked out. So the issue is that areas are positive. But I've defined my normal as being in one particular direction, and I'm taking my light source and I'm moving it 360 degrees, okay, in the 2D case anyway, taking my light source and I'm moving it around. That's going to mean that I'm spending an equal amount of time facing in this direction as facing in this direction. Unfortunately, areas normally would be positive, and this would be fine. This wouldn't be an issue. However, we're going to have a little bit more difficulty here because of the fact that, because of the way I've calculated this, I specifically used this dot product, and this dot product is based around multiplication. And therefore, we're going to find that this is equal to minus of... Okay. Which is a bit of a problem, because it means that the area I have when the light is shining from one side is equal to the negative of the area when the light is shining from the other side. And this produces a problem. It's not a huge problem, it's a problem we can fix relatively easily, but it does make me reconsider potentially my parameterization. Does it make me reconsider that? Okay, so basically it means we need to draw a diagram. So I'm going to take... So I'm going to consider our plane. Our plane was pointing in the Z direction, so it's facing like this. It's got an area of A, and what we need to basically ensure is that we're never going to, is that basically we only ever get positive values for our total area. What's the only way, actually, I guess we could do this just looking at the formula. The only way that we could get an incorrect, okay, I should write a little bit more in as well. So specifically, this is equal to the area of one face at an angle. I guess just make that a function of theta. I guess I'm also going to write a function of phi. I know it isn't actually a function of phi, but this will just remind me that, no, in general, that if I'd picked this coordinate system differently, it would be a function of both of those. So, okay, what do I now do? Well, what I can now say is that, okay, this isn't actually quite correct. So what do I do when I'm writing something that's incorrect and that I want to correct? I guess I could write a primes in front of it. Specifically, this is going to go negative at certain points in time. We don't want it to go negative. Fortunately, again, this problem is all centers around the fact that we're averaging. We are throwing away a ton of information when we take an average. We are compressing, in this instance, an infinite amount of information into one single number. And that's going to let us do a ton of things. Specifically, what it's going to say is that what I really want is, I'm going to want the integral. I'm just going to quote some parts of this because honestly, you can look up derivations of it online, but it's not hugely interesting. So an integral over an integral which weights every unit area on the sphere perfectly equally is given by this. Okay, that's what you might expect, but it's also got an extra factor of sine. How do I not know this? I should Google. I should just double check this quickly. Area element in spherical coordinates. I should not need to be checking this, but it's not something I ever memorize. Yeah, okay, I'm fairly certain I just saw what I thought I was going to see. I'm fairly certain I was right. Yeah, blah, blah, blah. The area element is, yeah, okay. Oh, yeah, okay, they're using a different convention to me, which means I should be scared and I should double check. Because I'm using the physicist convention. And this is an annoying thing in maths. Maths and physics. It's when there are different conventions and there's no clear way of understanding why things are the way they should be. But let's just double check I'm getting this right, because I don't want to do all this and then get the wrong answer at the end. I mean, that is kind of what I spend most of my life doing, so I would not be surprised if that does happen, but I'd like to avoid it if at all possible. And yeah, okay, this seems to be the correct formula, which is good. So normally what I would do is I would take the area of the shadow. I'm trying to average it over I'm trying to average it over all possible areas. So we're going to integrate this from our latitude. It's going to start at 0 and it's going to go down to pi. Sorry, our longitude is going to start. I don't know which is latitude and which is longitude. Hopefully you can work it out, depending on these. I know it's a little bit confusing, first off, when you see me integrating between two different bounds, someone integrating between two different bounds. The reason why we are integrating between two different bounds here is because the best analogy I've ever seen is if you imagine programming a robot to paint a sphere. If I tell the robot to go... great, how do I draw this? If I tell the robot to go a full 2 pi, or a full 360 degrees, go around all the way around to here, and then rotate an angle, and then at this new angle go all the way around and do the same thing, then if it goes a full 300, if it goes both fully around here and around here, it's going to cover every point exactly twice. It's really hard for me to draw because I'm not a good artist, but hopefully think about that, try and work out what I'm doing yourself, get a sphere, and see if you can convince yourself. If you're not comfortable with radians, 2 pi radians equal to 360 degrees, it's the angle system you basically have to use for calculus to work. So what I'm going to do is I'm going to calculate I want to take an average. What is an average? It is summing over a ton of things divided by the number of things you're summing over. So basically, what that comes out to is the area of a face at phi and theta. This is going to be the average of one face. However, as we've established, we're going to actually want to multiply this by 3. Because at any point in time, 3 faces will be illuminated. Unfortunately, we're still not done yet, because we need to consider the fact that, well, here I've got the area of the shadow of a face, but we don't have the area. We haven't worked that out. We've only worked out this thing which is close, but not quite. In particular, a face is going to be equal to the magnitude of a face. Normally, this would be really, really annoying to deal with. However, it's not here, because like magnitude signs, normally you want to run a mile whenever you see them. The reason why it's not going to be here is because we note that we know what the cosine looks like. In particular, cosine of theta is how do I want to write this? Let's just do this. Cosine of theta is greater than 1. Okay, I'm just going to consider between. I'm just going to consider this between 0 and pi, because that's the only range of which we're integrating. So between 0 and pi, cosine theta is greater than 1 for all theta, which is less than, pi of 2. Or 90 degrees. And we're going to have, conversely, cos theta is, I guess, cos theta is, I don't mean greater than 1, I mean greater than 0. And cos theta is less than 0 for all theta greater than pi of 2. And this is all theta within, I guess I should do, 0 less than theta less than pi. Okay. I don't know, this is concerning. Why have I not and realised there were more messages? Anyway, unless apparently my other laptop is not updating chat, which is a little bit kind of goes exactly against the reason I literally got it up. Anyway, what we can do is I can now split this. I can use the fact that integrals can be split up into 2 pieces, and what I can say is that, well, this is what I want. This is equal to this. I mean, that's literally just the same thing, but I can split this up. An integral is just calculating the area under a graph. Thing is, I can split that graph up into 2 pieces. And I can do. But here, if you notice something, I've split this up into 2 pieces, and in this first piece, cos theta is greater than 0, which means a of face is, well, that's going to be greater than 0, so I can just substitute this in. In the second part, we're going to have the exact opposite. We're going to be dealing with cos theta is less than 0, therefore this total at the area of the shadow that I'm calculating is going to be less than 0. And therefore we're going to get something that looks like this. What I can also, I guess, pull is another little bit of a trick with symmetry, which is that the area of the shadow doesn't actually depend whether the light's coming from above or below. You'll be able to see this if you like more mathematically and more rigorously if you substitute in the cosine theta and the sine of theta, and look at the fact that the frequency of the cosine theta times the sine of theta actually doubles, or you can just see it really like intuitively. It doesn't matter which side you're viewing it from, the area remains the same. In fact, that's a fact we've already used at least once. So I'm going to get this. and then all that remains is to actually solve the integral, which is, okay, annoying and tedious, and no one actually likes that. Let's just so the average area of the face, that's just relatively standard notation. Originated in quantum physics. I don't know it originated there. It got picked up very, very strongly in quantum physics. Yes, I can drop this in here. Okay, so now I just need to evaluate these two integrals. This last one I just know off the top of my head. That's 4 pi. Now that's just the area of a sphere of radius 1. The second one, I'm now going to... I need to think a little bit more carefully about, and I'm actually going to need to calculate this in a little bit of detail. So I'm going to need to substitute this in, and I don't know a nice way of doing this off the top of my head. And so my idea with this is that I'm going to, once I've finished deriving this and hopefully getting the correct answer, one way, I'm going to do it a better way. I'm going to see if I can come up with a better way. I have some ideas. I have nothing complete, but I do have some rough ideas of what I could do. I'll try and solve this problem. So, okay, cos theta, sine theta, what's that going to go to? That's going to go to, as it happens, cos theta sine theta is equal to a half sine of 2 theta. That's just a trig identity. If you don't know, you will learn it at some point. And, yeah, I don't tend to memorize stuff. I really hate the way my education system really prioritizes memorizing stuff. It's a thing I really, really hate about it, but there are certain facts you use so often that you memorize them naturally. So, okay, I should say first did that integral just goes to 2 pi, because it's an integral over 1, or it's integral of 1 over bounds, which are 2 pi in size. This one I'm going to need to change variables to solve. So I'm going to set that to 2 theta. I'm going to divide by another 2 here to cancel that out, and I need to make it clear that this is theta is equal to that. Theta is equal to that. At this stage, I'm integrating sine theta with respect to 2 theta. Anyone who's followed this far can almost certainly do that in their head. I can't because I'm an idiot. It's either cos theta or minus sine theta. I have to think about it from the derivative. So what's d? Derivative of cosine of theta, that's minus sine of theta, so we want minus cosine of theta. Yeah, okay, that makes sense. There's another quick way I could have come up with that, but the integral is going to go to this. Minus... Oh, I could have just done whichever one makes it positive as well. That would be another trick I could have used to do that. It's a minus, I'm just going to take the minus outside, and this is what from evaluated at theta equals 0 to theta equals pi slash 2. We're going to substitute this in. Okay, this gets, it doesn't give me 0, that's always a good sign. And in fact, it gives me a positive number, which is a doubly good sign. So I'm going to firstly notice that I've got a negative sign out front, so I can switch these bounds around on my integral. And yeah, okay, I've kind of lost the doing this all intuitively. This is just... It's just math to solve from what we had originally, but I'm aware this is not anything 3b1 would ever do or would ever condone in any science teaching video. So we've already lost any hope of 3b1's approval. Which, I mean, that's fine for you guys. Quite sad for me. So, okay, I'm getting the result. This doesn't look right. Oh, no, the 6 means it might be. Okay, so the result I think I'm getting is pi times a, or a pi. For this, which is going to give me a total result where a is the area of one of the faces. Which should, if I haven't mucked up any of my maths, which, I mean, I have, I can guarantee I never get maths right first time, which is going to be 3a upon 2 as a solution. If I've done everything correctly. So, the question is, well, is that correct? And is there a better way of calculating that? Some quick checks for is it correct? Well, it's greater than a. That's good. We on average expect it to be greater than a. It definitely should be. Should it ever reach 2a? Probably not. I guess I could work out the maximum value it could ever be relatively easy. What would be the maximum value? No, I can't do that relatively easily. It would require a little bit more trigonometry that I can do in my head. It's going to be less than... Well, it's definitely going to be less than 3 times a. Unfortunately, not quite correct, as you can say. Alright. I don't know... My issue is I don't know if that's due to the integration or due to anything else. There are quite a few... I could have just mucked up the integration. And I also don't want to turn this into just me debugging maths. You missed where pi disappeared. The pi disappeared when evaluating the average. So do you mean the pi in the denominator? Interesting. So here's a pi answer. The pi disappeared because we have the we had that full pi on the bottom. The pi came from the pi out here. The reason that pi at the bottom cancelled came from the fact that we had this pi out here, and this pi out here right at the very end. Yeah, so this pi came from the fact that we were integrating. The two pi's actually both came from the same place. And to show where they came from, I can just rearrange this relatively quickly. So I can do a face is equal to, and I can, because this isn't actually a function of phi, it is just a function of theta, I can get rid of that, and I can expand these out. Expand those out, and what I'm going to notice is that these two parts cancel, and these two parts were the only parts that gave us a pi. They both gave us a 2 pi, and those 2 pi's both cancelled. At least, assuming I did everything correctly, and so we end up with this. This integral is just going to be equal to 2. Yes, I kind of have that somewhat memorised. And this top integral I could have gotten wrong. I can double check this on Wolfram Alpha quickly. Or I could have set up the problem entirely incorrectly, which is also very possible. That seems span have come up on one end, but not the other yet. There we are. Okay, so, well, I mean, my main thinking was, can I come up with a nicer way of solving this problem anyway than the one I just used? Because, I mean, the way I just used was very calculus dense, and I know that was not what 3b1b's did, because he would never do that. And so my argument was that that then equaled area of the face I'm being hit by an or, is it? Can I not do basic calculus? Have I just screwed up my basic calc? Okay, I know I said no spoilers. If I've just screwed up basic calculus, please tell me, Zale. Because I'm more than willing to believe I have, because that is exactly the sort of thing I would do. Let me just... I'm more than happy to Wolfram Alpha this. Because, yeah, I screw up basic calculus all the time. That's what I do. Integral between 0 and pi upon 2 of... Oh, or are you saying... Oh. Something you would never do. Ah, okay. No, I can't imagine he went through... I'm just like confused. Yeah, I can't imagine. I can't imagine he went through much. I know, okay, he does calculus, but he does it very, very briefly. Or at least in the previous videos I've watched by him. So, okay, where have I can't come up with a flaw in the initial setup off the top of my head. The initial setup seems relatively fine. Am I off by a constant... am I off by a factor of pi? Is my real question. Because if I'm off by a factor of pi, that kind of tells me... if I'm off by a rational, by an integer factor, then that tells me that something about my initial setup and my argument about the face of the cube was wrong. If I'm off by an irrational factor like pi, that suggests something something more fundamental went wrong. Could potentially be my integration, which I should just check now. Get into this bit. Okay, I mean, yeah, Wolfram Alpha says that integral is equal to 0.5, and I'm pretty confident in... I'm more confident than I should be, knowing my track record of mucking up basic algebra. So let's just double check that the integral from 0 to pi of sine of theta is in fact 2. I'm pretty certain it is, and it is indeed. Okay, so the integral I've calculated correctly, and it's going to be fun if I've messed it up further than this, because that suggests my initial setup to the problem was wrong. And that's where I get back out of this maths and back into drawing more diagrams, and I feel that's more interesting. Do I want the answer to the question as to whether I am off by a factor of pi? Whether I'm off by something which is not... yeah, but am I off by something that's rational or irrational? Because that kind of helps me narrow down. Because I could go through and like double check all my algebra, but that seems like a bad idea, just in terms of anything being enjoyable to watch. So I'm looking back at my... So, okay, I guess that should actually be the area of all the faces. Or the area of the shadow due to all the faces, because this isn't the area of a single face, actually. So that should just be AS. I'm off by a rational factor. Dang it, that means one of my counting arguments has probably gone wrong. Oh, that changes something. Sorry. Yeah, okay. So I mean, I can roughly bound if this answer is off from the correct answer by a rational factor, then I can bound. Then I actually could just narrow it down to what the answer is, because I could just bound the answer. I could consider all rational. I guess I can. Okay, I consider all reasonable integers, and it's a 3 blue 1 brown problem, so it would be off by a reasonable set of integers, I think. When you say that, oh, you think it is correct? Brilliant. Okay, if this is correct, then this is where the fun begins. Because okay, I think that's correct. That's good enough for me. Because, I mean, I guess it doesn't... It's kind of nice to know whether or not that's correct. But that's not the fun part. The fun part is 3 blue 1 brown's videos are amazing because he comes up with the cleverest ways of visualizing problems. Also, thank you so much, though. I know you should be asleep, and I appreciate that. It comes off the most fun ways of solving problems. So what I want to work out is what's the better way of solving this. So what we're dealing with is I'm just going to convert down... Actually, this is a technique I never use, but I see 3 blue 1 brown do somewhat regularly, so I'm going to give this a go. I'm going to convert down to a much, much, much simpler problem. I know I can take a face of shape. So basically, I want to come up with a better way of finding the average area of the face of a shape. And I know that the average area of the face, well, that should come out to A over 2. So, yeah. I want a nice physical argument for why that should be the case. I could come up with arguments that are equivalent to just directly doing the integrals, i.e. rotating and averaging in my head. Like, I could come up with an argument like that, but that's cheating. I'm not going to allow that. That's a bad argument. So, how else do we do this? What I would love to do, and would be like a classic 3b1 solution to the problem, is to consider a point of light. Basically, I want to do something which somehow implicitly sums everything simultaneously. That's the aim. So because that's what averages lose so much information. There, I almost guarantee, is a way of phrasing this problem with... no, I think I can rigorously mathematically guarantee there is a way of phrasing this problem with a finite number of light sources. Or, not a finite number of light sources, sorry, but with just considering the shadow of a single object. That will be doable. And that's kind of what I'm looking for. Or, slight voice break. Or considering the area of something else entirely. Okay. Okay, I can come up with a way of rephrasing this. I don't think this is an interesting way of rephrasing it, but this is directly related in some sense to the area. Okay, at least in 2D, this is related. Effectively, what our maths was doing is we took this line, 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 etc., and we summed up the shadows of all of those. Let's imagine we actually, I mean, more rigorously for what our maths actually did, we only went to like this, and we just used counting arguments to get the remainder. But we could do this another way. I could, rather than laying them out end to end like that, I could lay them out like this. Or something like that. That seems interesting to me. Because then I only need to consider light coming from one direction. Not only do I... no, this just comes back to doing the integral. So, okay, yeah, what I could do is I can do this. I was hoping I could get away, I could come up with a clever way of arguing this, that this wasn't equal to the integral, but it will always be. I was thinking I could do this, and like this is a cool geometric argument for it, so rather than considering all the planes separately, I can actually put them together, build a single object out of them, then I can just use the fact that what the area of the shadow is equal to the area of the shadow of this line. That's relatively easy to work out. But unfortunately that comes down to being precisely equivalent, I'm fairly certain. So, okay, what happens if we try and generalise this? What happens if instead I look at a tetrahedron? The counting argument will be different. The counting argument might actually work the same with a tetrahedron. Wait, is this the same for a tetrahedron? What is it? Okay, and let's get rid of that. Yeah, I think this can't be the same for every object, can it? No, it definitely can't be. Okay, yeah, just consider a tetrahedron for the second. So where does this go wrong for a tetrahedron? Oh, I see where it goes wrong. Okay, so a square had a relatively interesting property. And the yes, I've just split. That is like the most cursed way of splitting up those faces. Yeah, a square has a really interesting property, which is that when light... When light falls on a square from one direction, like this, or from any direction, virtually any direction, not every direction actually, there's one counterexample, but almost every direction, the light, we can basically convert by a rotation the light being the shape which is made by the side the light hits, and by the sides that is shadowed by the side the light hits. And we can rotate one onto the other. They're rotationally equivalent. Here, this isn't the case with a tetrahedron. The question is, does that matter? And the question is, what part of our arguments does it change? Yeah, it does matter, I think. Oh, I've got to be careful with this. So this is where the problem gets interesting, because I almost guarantee this is the kind of generalization he will do to get the answer. So you generalize it down into a much simpler shape, or something like that. Okay, so let's try this argument again, but for a triangle. We do have precisely the same argument must hold about light coming from two different sides. This just makes a lot less intuitive sense to me. But the area of the shadow, no matter for parallel and anti-parallel beams of light, must be equal. I think the issue is this is just much harder to visualize for me. But okay. So we are turning, when we look at the problem for the tetrahedron, we turn this. Okay, so this is only going. This is difficult because there are issues. This works quite well for the tetrahedron, or the logic I was about to present works well for the tetrahedron. But let's just consider a pentagonal prism. There things get really weird when you start having. There, like, the number of faces can quite significantly change. The number of faces illuminated. I guess that changes between 3 and 2. Well, the issue is just you have multiple faces illuminated. For a square, I guess for a square you did have. For a square you always had 1 or 2. So the number of faces illuminated at any point in time changes. I mean, the total area for a tetrahedron must be less than that for a square. It can't be equal. This is at the stage where I think this is too late for me to come up with something, which is annoying. I think this is the key, though. I think this is the key to solving this problem, like, in a neat way, is considering what happens. What do I mean by total area? I forget the context in which I said total area. What I'm looking at. So, yeah, okay, yeah, my issue. How large is the tetrahedron relative to the square? I was going to take them to both have faces of the same size, A. So then it's not actually same side length, surface area, or volume, but the same side area. And what I was wondering is, it feels like that. It almost feels like that should come out to 3a over 2, because I don't actually see the total area for a tetrahedron must be smaller than that of a sphere. If I said sphere, then I was definitely talking the wrong thing. I probably meant to say square. I probably tried to say square, said sphere instead, but I actually meant to say cube. Because you're just going, when you're dealing with a tetrahedron, I guess my intuitive reasoning for this is when you're dealing with a tetrahedron, you're going to spend more time only illuminating one face. In particular, I can envisage a shape that looks, well, I can go back to something, I mean this is in 2 dimensions, but something somewhat pentagonal, and you can see that if the faces are all of the same area, then most of the time, or all of the time, for a pentagon, we're going to have 2 faces illuminated. For some of the time, okay, this is in 2D. For some of the time, we're going to have 3 faces illuminated, so the number we get must be somewhere between 3a and 2a. do. Whereas for a tetrahedron, for a triangle in this instance, I know it must be bounded by A is greater. Oh, this is kind of interesting. A is greater than yes. Sorry, A is 2A is greater than AS. It's greater than A. That argument is interesting and weird. That argument shouldn't hold. I don't like that argument. Does this only hold in 2D? Because that argues... Oh no, okay. Okay, good. It doesn't have to... Okay, the total area... Okay, the total area for the quadrilateral does not have to be greater than 2A. I don't think. Yeah, because, yeah, it only has to be greater than this line. And rather than 2A, or at least with the argument I was making, I was just taking the largest possible area and the smallest possible area, and those are not what I've written up there. Okay, that's good. That's good, because that at least means that I'm not being a complete idiot. Okay, so how do we go about... How do we go about the problem? This problem, then. This is interesting. Okay, so we've... This is a quick... I'm just going to now come up... Yeah, they should almost certainly be greater than or equal. No, because well, if I'd done my maths correctly, they should have been greater than, because I knew there was some element that was larger within the set. I just didn't know how large that element was. Unfortunately, my entire maths was wrong, so it didn't really check out anyway. So yeah, I want to use a similar argument for this problem. For the problem of considering, okay, at least a triangle or a triangle, then maybe a tetrahedron. Because it feels like it should just be a different counting argument. The issue is it was so nice for a square. So what was the... Okay, let's just do it in 2D, because I don't want to have to draw a tetrahedron. And it's getting late and my brain processing speed is decreasing. So my argument was, okay, we start with this. We argue that, okay, I can firstly split that into this. My argument was then, from there, we could that problem, or the problem of adding that and this was equivalent, or that eliminating that from both sides was equivalent to eliminating this. It's equivalent to doing this twice. The issue is that it's a bit harder to make that argument for this second case. Okay. What I could do is I could work out maybe the average number of faces visible. I don't think that's... No, I was thinking average number of faces visible and average light instant on each face, but the product of the averages is not the average of the products. So that really doesn't hold. I mean, it might hold in this case, but I haven't shown it to hold. Yeah, no, I definitely will still want to keep that times 2. Okay, so where do I go from here? I may actually just see tomorrow if any of my physicist friends are free and see if they want to also take a crack at this, see if we can come up with something a little bit better. Yeah, and then so the argument was we went from that. Oh. Okay. Okay, I see where the issue is. Where I'm having difficulty moving between my two arguments. It's because in this argument I moved in 2 steps. I converted. Okay. Okay, so we have 3 sides eliminated at any point in time. I guess, yeah, the issue with the tetrahedron is that you don't have the same number of... Is that there are like different cases for how many sides you could have illuminated at any one point in time, and that wasn't the case for the square, for the cube, rather. Let's just double check. Yeah, so the issue is that I can draw a tetrahedron from this angle, and I can also draw it from this angle. And there are a different number of sides visible in both of those. That's what makes the tetrahedron problem harder. Because I can't just say we always have 3 faces visible like I could with the cube. That's annoying. Okay, so there is something actually somewhat special about the cube. There's something about the cube that makes this problem easier. Okay, so maybe it does then come down to, so I don't think I can do it by I kind of want to do it by considering all shapes, but I don't think that's the nicest way to get an intuitive answer. I think there was some good intuition up to the point of saying the average shadow of this. And I then want the nicest way of calculating the average shadow of that. One thought I had was the cube sometimes has 1 or 2 faces visible. Yes, it does, but only for an infinitesimal amount of time is the issue. So yeah, the cube sometimes does have fewer faces visible, but it's not for long enough for it to contribute to the integral, and in fact, the value comes out the same. You could actually treat it as being one of these faces being slightly visible and the other one not being visible. The area is equivalent if it did have 3 faces visible. The function's basically continuous. If you imagine I have a tiny angle here, epsilon, and that's the angle the light's coming in at, then there I would have, okay, this is a square, so in this case it's only 2 faces visible. But yeah, then for starters, it's an integral of something that only occurs over a small area, but even if it weren't an integral, it would still be continuous, and we would still get the same value for a subface. I don't think I can make a similar argument. Yeah, I can't make a similar argument for the tetrahedron. So it can't be equivalent to the tetrahedral case. I mean, it would be really cool. So I feel I can split the tetrahedron into 2 cases. But I feel if I have to split it into multiple cases, I'm getting further from a unified answer. And if I do it for any general polyhedron, I'm going to get even further from a unified answer, because I'm going to need to consider all of the faces at once. So I think I should try and come up with... I doubt this will be 3b1b's answer, but I don't see a way forward of doing this at the moment. So what I'm wondering is, can I just deal with a single square at once? Imagine throwing a single square up into the air, and it spins for long enough that it had... Okay, there's one other problem it's equivalent to, but the issue is I've got to try and make something that it's not trivially equivalent to. So, an almost trivial equivalence is if I imagine taking an infinite number of infinitely thin sheets of paper, or which like have partial transparency. In fact, they have infinitesimal absorption, and I consider basically scrunching them up into a ball. I think I'm just going to have to go and watch the video. I'm relatively pleased I managed to get the area of the shadow, and in a way that generalizes. So I feel I could generalize that formula relatively easily. to a hypercube, which is kind of cool. So if I wanted to deal with a hypercube, we would need to have changed the number of faces. The number of faces is going to be, I can't type, so I'm still drawing. Yeah, the number of faces would be in n dimensions. It's just going to be 2n faces. Can I do? Then you can finally go to bed. Yes, you should. I feel tired, and you're an hour ahead of me. Yes, so I mean the number of so that's what I suspect it is for a hypercube. So I think it's just going to be a case that the number of faces, the number of faces illuminated approximately at all points in time is the same. Yeah, okay, so that's actually really cool. So for a hypercube, all of the arguments hold basically identically. Because you're still only because you still write things in polar coordinates in an identical way. You still have some stuff up here, you then have some stuff, and then you end up with a cosine of theta, or a sine of cosine of theta. And now it's not going to italicize my theta because I did that. Oops. Yeah, okay, so so the answer for a hypercube we can work out, which is this. But which is a nice little addendum. But yeah, I should go to sleep now. So they all should definitely go to sleep now. I should watch the video, and I should see this. Yeah, I'm interested in seeing how he does this neatly. Honestly, I'm really excited because I think this maybe solves a problem I actually had a while back, which was the average number of times light bounces before leaving a cube. And that's really it feels quite closely related to this problem. But yeah, so I've got a huge thanks to give to Sale for reminding me that I wanted to do this. I hoped I'd get something a little bit neater. Maybe I will do this with some more friends at some point and see their ideas thrown into the mix. Or maybe with someone who has watched the video who can give me hints as to where it might be interesting to go. But anyway, yeah. Huge thanks to Sale for actually sending that video.